So I want to welcome everybody to our monthly BioPACIFIC MIP seminar series. I really am excited today to introduce our seminar speaker, Professor Jason Hein. But before I do, for all of those of you who are not familiar, I just want to remind everyone, right, that part of this seminar series is exposing you to BioPACIFIC MIP, which is this national user facility really dedicated to high throughput manufacturing, high throughput synthesis and characterization so that we can discover new biomaterials. And the user facility is at UC Santa Barbara and UCLA, and we have 5 different areas of thrust, right? The living biofoundry, synthetic chemistry, additive manufacturing, characterization, and data and computation. And so if you're not already a member, right, I really encourage you to join our mailing list. This will allow you to keep up to speed. Things like our upcoming summer school will be advertised there. And so really take this opportunity to use this QR code or go to our website at biopacificmip.org to learn more about this. And so with that, I want to welcome everyone to our seminar series, and I will stop sharing and let Jason put up his first slide. And while he does that, it'll give me an opportunity to really introduce Jason and tell you one reason why I'm so excited to hear about his talk today, which I think encompasses many of the things that we're trying to establish here within BioPACIFIC MIP. And so by a little bit of way of background, so Jason did his bachelor's work at the University of Manitoba, and then he stayed there for his PhD studies under the guidance of Professor Holton. After that, he moved close to us down the coast to Scripps in San Diego, where he did a postdoc position first with Barry Sharpless and Valerie Fokin. And then after that, he also became a senior research associate with Professor Donna Blackman. And so what you're going to see is, during those evolution of his PhD work and postdoc and work with Donna, he's kind of has expertise in synthesis, characterization, as well as really studying and leveraging the power of organic transformations. He started his independent career in 2011, just up the area from us at the UC system at UC Merced. And that's where I actually got to know Jason. So Jason and I worked together early on in both of our careers, and really I got to experience how much you can learn by monitoring reactions in situ instead of just taking random time points and then trying to stitch together what might be happening with the mechanism. Since then, his group has really transformed, and in 2015, he moved to where he is now at the University of British Columbia. And I think he is one of the pioneers in thinking about flexible automation to really tackle some of the challenges in organic chemistry and materials and where those fields intersect. And so with that, Jason, thanks for agreeing to be our seminar speaker today, and the floor is all yours.
Thanks very much, Javier, and yeah, really appreciate the opportunity. So today I'm going to tell you actually a whole wide swath of different things. I want this to be an introduction to kind of what we do, but more importantly, how these tools and technologies we're building can be implemented in a whole host of different sort of application spaces. Javier mentioned, while I still am, I consider myself a physical organic chemist, but the tools, the data handling, the AI, the other components weren't quite ready for our direct application as mechanistic organic chemists. So what we've really done as a group is kind of go it sideways and look at how these tools could evolve, but more importantly, how they deploy and apply them to our day-to-day. Really, as in the title of the talk, the thing I want to introduce you guys to is the concept of flexible automation. This is something that actually a colleague of mine, Curtis Burlingett, and I published a quick perspective article on this in Nature Materials earlier this year. And the thesis of the article was really to try and explain to people that what we're doing in this concept of flexible automation is it's actually distinct from high throughput experimentation as a classical. While this is something that is a little bit more mature of a field, the concept of what we're trying to do here is to say that, look, your day-to-day series of experiments, what you want to apply this to, and the tools themselves are actually rapidly evolving. So fit to purpose and really dynamic sort of applications is what's the name of the game. The concept we're trying to say is that, look, if we're going to take a conventional prototyping and piece of automation, something like let's say a ChemSpeed reactor platform, there's a possibility that if you're trying to bring that up to a fully autonomous or fully automated workflow, this takes many, many months or years even to potentially design, build, and actually deploy it. And the problem with that is the issues and things that we're trying to deploy onto are changing so rapidly that those kinds of pieces of toolkit are almost obsolete by the time they hit the sort of the bench. The experiments have evolved and things have changed in such a way that in the ensuing time of kind of getting the kit ready, the target's now different. So what we've been advocating is actually really interleaving these design, make, build cycles of both on the hardware and the experimental design side to kind of get going faster, but also allow it to evolve as the needs of the experiment evolve. And I'll take you through a couple examples of that. So it's really just saying that, look, we can borrow from this idea of rapid prototyping, 3D manufacturing, and basically upgrading and evolving on the fly so that the tools and the robot itself is actually one major part of the experimental kit. As an example, this is kind of what a tool chain kind of looks like, where fundamentally we're always going to have some type of software, hardware balance, but the experiment and planning side of things is something that's changing rapidly. And again, to really hit that wide strike zone, it means that we have to think about where these things can be deployed. Why we care about this is really to sort of take the automation, not only just to make our lives better, to search a wider experimental space, but it's really to actually start to interleave this with what's the major uptick we've seen the last couple of years with machine learning and AI. The capabilities and capacity in this are starting to become something that a wide variety of users could start to actually sort of tap into, which means getting this kind of this fully autonomous kind of research aspect is possible if the hardware where the actual experiments are being done evolves in the same sort of way. Now, where it sort of stands and why we're kind of building this is we're trying to really focus on this concept of a self-driving lab. This is a hybrid system that's both capable of executing, analyzing, and then decision-making, so that basically you can actually give it a target on optimized yield, a particular property, something that would actually encompass far more than just you sitting down, running thousands of experiments and churning through the data. It's actually to sort of do more of small group analysis guided by an algorithm. So it has the advantages of some of the sort of smaller single manual experimentation in the sense that it can be very, very flexible. It can change rapidly, and you can actually sort of guide it to better targets. But it also has the advantages of the more HTE space, such as high reproducibility and faster experimentation, 24/7 operations. So it's meant to kind of hit in the space of sort of best of both worlds. Now, this is also not science fiction. There's actually a great article in Chem & Eng News by one of my colleagues talking about the work that Alana Asper-Guzik at the University of Toronto has been doing. So I really encourage you to go take a look at this. This is really trying to be a first pass in this space, talking about how these self-driving labs are beginning to proliferate, and they can be as complicated as a massive entire facility, something like you should see it sort of like Emerald Cloud Lab or something like that. But it can also be as simple as an algorithmically driven system on your benchtop, or even systematic applications of how you go and do experiment using a semi-human in the loop kind of optimization, where instead of doing what might be multivariate design of experiment, you would apply one of these kinds of general algorithmic searches. So to kind of ground everybody, some papers I really, really like from this space, if people haven't started to see how ML folds into synthetic chemistry. This paper by Frank Glorious is a great introduction for how ML can sort of help around synthetic optimization. This paper by Daniel Recker and Tiago is a great sort of perspective on how an algorithm, which is a fully free sort of toolkit, can be used to help really diverse set of experiments. If you're not familiar with it, the work by Abby Doyle is fantastic in the sense that she's created a simple GitLab downloadable batch Bayesian optimization engine, which is really focused on helping synthetic organic chemists think in the sort of ML data science kind of space. And again, this is something that if you've never worked in this, it's a great introductory toolkit to get going. And then finally, a much broader review from the materials community led by Benji Murayama from AFRL, talking about how autonomous experimentation is starting to revolutionize material design. Now, within our own lab, we've had a couple of these systems come online. We were actually one of the first labs to build out what was called a Project Ada. This was a self-driving lab that was made on doing thin film type materials. It was focused on looking at solar cell components, specifically in the whole transport layer. And its job was to sort of look at these really complex physical organic space, but also property type measurements. And this gave us the template for how these kinds of labs had to be built. And really, it's inspired this whole idea of flexible automation, because the constant question we got at this time was, well, how much does this system cost? Or how could I apply it somewhere else? And the answer was, it depends. It is a really, really bespoke system for whatever application you're dealing with. And there's no one single answer. It's more of a philosophy than it is sort of a clone. To kind of highlight that, we use the same concept embedded at Merck process chemistry to come up with a batch Bayesian optimization system to look at selectivity and yield in a Suzuki cross coupling. So very simple. The first one was a material design problem. The second one is actually a synthesis selectivity and optimization problem. And it was executed using a ChemSpeed, so commercial hardware interfaced with HPLC analysis. And this was published earlier last year in communications chemistry by my student, Melody Christensen. So really within my lab, what I'm going to tell you about today is the bits and pieces that we have to put together and to evolve in order to make these things possible. The first is the analysis. We've been very heavily engaged, as Javier mentioned, about in situ analysis and sort of bringing that to the forefront. And we have a whole series of different hardware on this, specifically around online HPLC is our major toolkit. This particular paper talks about how we were able to adapt this to actually monitoring systems live by reactions that were actually being done with pyrophoric materials in a glove box. Second is really the tools themselves. Each one of these kind of kits is only possible by taking either automated or something that can be automated and put it together, which would normally represent an experimental step. So weighing, solid dosing, liquid dosing, stirring and heating, and then other components like computer vision or image processing is only possible by having sort of these modules put together. So in this design, this iScience paper, we built a system that was capable of doing solubility measurements by simply looking at reactions and saying, is it dissolved or not? So it's making a judgment based on dissolved components using computer vision. Finally, you got to run the thing. And as organic chemists, most of us don't come to this with a lot of programming tolerance or programming flexibility. So building ways of interfacing with these systems is important. What we did in this JChem Ed article was actually show how voice assistants such as Apple and others could be used to simply talk to the automation. So this was actually a titration experiment we built where students could actually join a Zoom call and natively speak to the equipment in order to do experiments like add material, turn on the dose, add the buffer, or something like that. So they can actually only interact with it in a native language capacity as opposed to having to learn how to code or use a piece of software. We had this perspective article in Chemical Research where we're talking about where automation fits within this broader ecosystem of now data science sort of coming online. And particularly for us, it's that data piece, right? AI and ML eats information and good information, and having automation linked to this is critical to sort of really accelerate what we're doing here with this interface of data science. And finally, it's just getting these things up and running. Taking a reaction or a tool chain and making it automated is not a single path. There's actually quite a bit of forethought that has to be done. So we wrote an article in ChemSci earlier last year that talked about how you have to sort of think about things prior to doing a fully automated workflow. But more importantly, again, I really want to thank my group. This is actually one of our first post-COVID pictures. The team here is just this phenomenal group of sort of computer scientists, synthetic chemists, chemical engineers, mechatronic engineers. This fusion of different interdisciplinary parts is what makes it possible. And I want to highlight some of the work that many of them that have been done today. But also, in addition, if you're interested in learning a little bit more about what we do have a YouTube channel for the lab. And what we like to do with this is to actually sort of show off the kinds of things that they have capability on. A lot of the stuff that we do, some of it is experimental focused. Other things, the students just really like to use this as kind of showing off what they had. This is a particular holiday video where we're using our robotic system to actually create a colorimetric titration for the level of chocolatiness based on an image algorithm to make a particular kind of hot chocolate on our hot plate. So again, please follow what we're doing on that. It's a great way to sort of keep track of the types of things that we're doing in the lab. So first off, I want to show you through how we kind of take a standard experimental tool chain and turn it into an automated one. This is an example of something that kind of the timeline that usually we're turning around on. So we have to go from an initial ask to a delivered product, usually in about 4 to 6 months is what we're kind of hoping for to have sort of a first point. And then we evolve from there. In this particular one, we were asked to come up with a system that could be capable of actually designing or doing a self-optimization around a fully autonomous synthesis of gold nanoparticles, specifically nanoclusters. So where we start was an ask comes to us. And the very first thing to do is to look very detailed about how it's done today. What are the steps that an experiment or an experimental workflow, what does it actually look like right now? And often that really looks like taking a cell phone, going to the lab and just showing in detail every step one might do using a normal conventional sort of point. So what we did is we had the collaborating group come to us with these 10 little MPEGs, and they're showing through the individual steps that we required to do this whole part. So what we get from that is now this kind of a hit list of what are the individual experimental sequences that have to happen, and we map that against what we can do right now. So this is where we go back and look at our equipment and say, okay, we currently have the ability to do liquid handling under a bunch of different capacities. We can flexibly control that. We can do solid dosing. Okay, we use these particular things like a methyl Quantos. These are industry standard powder dosing components that are not part of some locked off or closed system. It's something we can interact with. We have heating and stirring, and we have a variety of different arms. Now, what we also do is we identify the things that are missing. In this particular case, this new ask, we had no ability to do the sort of workup and purification. The isolation purification required a distillation, a solvent removal, filtration, sonication, and centrifugation, which were not immediately at that kickoff time things that we had some solid grasp on. So what that meant is we had to go back and look at each individual step, finding a way to sort of map over that. So this is a case where the first solvent removal was actually done by simply taking 2 zones, a hot and a cold. We actually connect the two by way of a cannula. So this is a cannula the arm can actually pick up and stab in that point. The reaction's in here, and what we're doing is we're blowing air or nitrogen through this point. So what we get is actually something that's akin to a little bit like a rotovap kind of strip, but we're blowing down, heating one zone, cooling the other with a positive place displacement. This allows us to strip the solvent. So this is a first fit to purpose fix based on bits and pieces we have around the lab. It didn't look like what the lab would normally do, but it allows us to sort of move forward with this step. So now the robot has the capacity of doing a solvent swap. The second, we have to do a filtration. This is a gravity filtration typically. So what we end up doing is just working with something like a SEP funnel because we have this nice conical bottom, and we can actually go back and just teach the robot to simply pick up and dispense. Now, what's interesting about that particular motion is we can actually add these very sort of anthropomorphic things in, such as at the top of this point, if you notice, we shake. That shaking is specifically done there to actually do exactly what you would do in the bench, which is, tip, move, shake, or basically dislodge any drops. So having components like that allow us to rapidly do something that we would normally be used to doing. Again, is it what we're going to do all the time? No, but it allows us to sort of have a first design principle in place very quickly. Next, we had to do a sonication. We did not have an automated sonicator, but what we do have is a relay. We can turn the sonicator off and on. And because the arm has this infinite spin wrist, what we can suddenly do is turn it into something like a rotovap. It can sonicate and spin in this bath, turning on and off the sonicator by just using a simple on-off relay. So now the deck has all these individual capabilities into it. The last one is to get far more complicated, and that's what we're doing here. We're actually taking the system from one deck, passing it to another robot. The scarer arm then picks up the sample and passes it to a different arm. That final arm's job is to actually interface with a centrifuge. This is just a simple benchtop centrifuge. The problem we have with it is there's no way of knowing where that position is or where the deck position is. It's not an index thing where we know which position on the centrifuge head is oriented in what place. So this is where we use things like computer vision. Simply seeing what's happening on there by putting a couple of dots and using a simple algorithm to calculate the angle that those dots make allows us to go through and do an action where we actually pick up a finger. That's what we're doing right there. We pick up this finger and we reorient it, move the head so that it's in the perfect position. So instead of having a very complicated or expensive sort of encoded head, what we can actually do is do what you would natively do, look at what position the head is in, adapt to it, and then place it in a position based on your visual cues. So this has actually been a very rapid way of sort of adapting this in, is to add something like computer vision to some kind of component. So with this, we actually get the full experimental series. We actually have the end-to-end workup done. And this is actually something that's the full video is now on YouTube also. So if you'd like to go take a look at our entire series, we have this sort of end-to-end workup, isolation, filtration, and centrifugation kind of workflow all built into it. So just wanted to pause for a second about this thing about vision. Vision is absolutely critical when it comes to this kind of mode of operation. Not only is vision pretty typical for things like image analysis for high throughput experimentation, like manufacturing robotics, but self-driving cars use things like vision and visual analysis quite heavily. There's categorization that's very rapidly possible by building ML models to sort of say that, you know, in a picture, what is ripe and what is not ripe. And if you've ever visited an Amazon grocery store, it's really interesting because there's no people there as clerks. What you have is ML vision algorithms running to basically know that who you are and what did you pick up and what you need to be built effectively. So using that kind of point, we've actually done quite a bit in this point. An early example was this paper in Chem Archives, where all we're trying to do is build a simple Python package to watch the level of liquid inside a reactor. And what that lets us do is actually use that liquid level to do feedback and pump control, which then can be used for a variety of other experiments. More particularly recently, though, we've gotten a much more complicated and comprehensive version of this. Computer vision is a very simple way to interact with pieces of hardware that you don't normally have serial control or other sort of automated feedback. So as an example I gave you before was the centrifuge. The other thing we can do is, for example, a pH meter. Normally, you're used to looking at the screen on a pH meter in order to interact with it, right? And there are some that you can buy that have serial components and other data API, but that's not always guaranteed. Sometimes these are hardened systems. Sometimes the proprietary vendor does not allow you access into it. So what we can do is actually use the simple things like Google Tesseract, which is a very easy OCR, optical character recognition algorithm. Having a simple webcam and Tesseract, we can actually take that screen and deconvolute it into images to do a text recognition. And now we have a way of sort of pulling information off of just a simple component. You have to get a little bit creative. So for anybody here in the audience, if you can notice, this is what we would categorize as a good image, and this is a bad image. And what we mean there is that we have to come up with a small sort of error checking algorithm. If you look closely over here, we're missing this period. So what happened is, as this particular instrument is being used, if it is taking the measurement, it hasn't stabilized, that dot is not shown yet. And if it is still in the process of making a measurement, the dot is either flashing or missing. So we can use small visual cues like that as part of the decision algorithm that says, if the OCR recognition is missing that dot, don't take that experiment or don't take that number. It's not ready yet. So we can continue to take measurements until that sort of characterization is met. So we can add these other pieces into it to make the measurement far more intelligent. In the same way you tell an undergrad or your first sort of a person working at the bench, don't record this number until you see blank. That same sort of logic can be built into these things quite easily. At the same time, too, we can actually build other things to patch up over. Now, what I mean here is Tesseract does a pretty good job, but however, what it'll do sometimes is misread the decimal as a comma, or it'll see a 1 as a slash or something. In this case, it thinks the 7 is a slash. By adding other native things, such as, look, the data format must have this particular point, we can actually have these correction algorithms in to do string replacements. What this just is trying to represent is, instead of stumbling because the simple thing you put on there doesn't work perfect out of the box, you can add these catches to it that actually allow something that might only have a 50% success rate to quickly jump up to 90-95% success just by having these other sort of nascent patches built in place. And what it allows us to do is take a simple syringe pump, stir plate, and webcam, and take a standard pH meter and turn it into an auto titrator very, very quickly. So it has the capability of now doing native dosing to hit a known pH, or even to do a full pH titration curve in a fully autonomous way. The next thing I want to talk about is taking this concept of feedback and putting it towards synthesis. So here, what we have is we're talking through how we apply this to something like amide bonds. Now, for chemical and the chemists in the audience, amide bonds are one of the most prevalent reactions seen anywhere in pharmaceutical science, material development, biological chemistry. So knowing how to do this well is actually big business. What's important, though, is you kind of have, just like doing things like cross-coupling, all these reactions that are very, very useful. There's a million small different ways to do this specific thing. So simply activating groups, if you only look at how you turn a carboxylic acid into some sort of an activated component, you have a wide variety of different possible reagents to do that. Each one has its own nuance in terms of its cross-reactivity, how you do that activation, what type of solvents are compatible to it. So it gets to become a very complex problem. Then, and even at this stage, all we've done is made the activated ester. We still have to go through and do the amide coupling. So the thing we were challenged with is we had this subset of 20 carboxylic acids and 17 primary amines. And again, this isn't really even getting that structurally complex. We're only looking at NH2 coupling to carboxylic acid. And the ask really was, come up with a way to measure the rate of amide bond formation after the activation has already taken place. So we really care about activate the carboxylic acid to some efficient way, get to a common purity and start state, and then do that amide coupling where we care about really the rate of the amide coupling, not about how that activation condition was actually executed. If you do every single one of these cross points, that's over plus triplicates. We have over 1,000 experiments we have to do, and that is far beyond sort of the capability of what we'd have now. And if you also look at this from the something like high throughput experimentation, the individual parameters around what every one of these would look like is different enough that if you tried to do this on a plate, you'd have a lot of failures because certain solubility requirements come in, some activate very slowly, some are very fast, different time regimes. It's not something you can put one protocol over top all of it and hit all 1,000 experiments with the fidelity that we needed. So the goal we really wanted to focus on was, okay, we have to execute this first step, really study the second step, which means everything about that first step must be done such that we have a common landing zone for that second step to be nascent. And really to do that, what we need to do is actually onboard a whole ton of process analytical technology to really ask the question, if you were a graduate student or a researcher going in to do this, you could do it if you knew that it was the right time to do that second step, that the experiment had finished executing, that the yield was at a certain level, that everything was at the right time. So normally what that would mean is you would interact with it, you would look at HPLC or TLC, and we need to give that analytics and decision-making capability over to the hardware. So we chose to use React-IR. What that lets us do is see both the consumption of things like our starting carbonyl, but it also allows us to monitor CO2 in the system. This plays a very important role for things like CDI coupling of amides. What we can do with this is we can actually dose in an extra amount of CDI, drive that activation to completion. When the system knows that it is now at a certain threshold, we can destroy the rest of the CDI based on a calculation of how much we think we've used based on the CDI signal from IR, and then watching the CDI be fully consumed at that time. Most importantly, destroying the CDI without touching the activated ester. So this is a titrometric measurement that has to be done on the fly. The whole system ends up looking like this. We have the full capability in reactor, plus the ability to actually monitor this online. So this is where we're bringing some of our online HPLC capabilities in line as well. The system now has the capability of not only setting up the reaction, adding individual components, but because it's using HPLC, it can actually interpret the HPLC as, okay, if I do a blank injection after I've added my carboxylic acid, I know this new peak that I see here must be my carboxylic acid peak. As the CDI is charged, it now knows this new peak I show up must be my activated ester. So we don't even have to program to watch for single bands on the HPLC. It's actually running in the background, interpreting the HPLC, and then assigning new peaks to their particular roles based on the chemistry that's happening too. So what that lets us do is very flexibly provide it with rules and goals. So instead of saying, take this vial, add this much at this time, it's being given descriptors like, I want you to create a stock solution. I want you to create a calibration curve. Initially, I want you to wait until your starting material has decreased to this level and you see this new product. So again, it's native meant to be the same kind of instructions you'd provide to your researcher or colleague, as opposed to what we'd normally see on innovation deck. So this particular work has actually now sort of built out this kind of a tool chain. What we have here is a single experiment that has standard deviation and calibration. So we actually are building our extinction coefficient concentration curves at the beginning of the reaction. We have our activation part. We have our changeover. This is the destruction of the extra CDI, purging of the CO2 at that step 2, and then the charging of the amine, which really what we care about here is the relative rate of the formation of this component here, where at the end of the reaction, we actually calibrate the concentration curves that we get from the amine as well. All those checks are built in. This can be done flexibly for any of our particular ones. Taking this through, we actually did a whole bunch of different combinations. This is just a subset where we have very different rates of activation coupled to different amidation. And we're really following sort of the rate of amidation here in this second step. This work was actually just accepted in chemistry, sorry, I forget the name of the journal right now, but it has just been accepted. It should just be up on our website at this point too. Chemistry methods, excuse me. So it's talking about how this kind of adaptive automation potentially is a better way than when you want certain kinds of data. It's a different sort of technique that can be used in addition to standard high throughput experimentation. So it allows us to look at this part over. Now, where this kind of data would be useful sort of pairs into what we've seen with Matt Sigmund's lab. So having absolute rate data like this can actually be used in various sort of linear free energy kind of models to really start to predict what combinations might look like something else. So it's really, we're after that data set. Once again, we have this full robotic platform, and its work through is on our YouTube page. If you'd like to look at what steps kind of happen in what kind of order, again, please do check that out. So the last thing I want to sort of focus on too is taking this out of the lab and actually putting it into a much more real world problem. In the last couple of years, I'm sure you guys are aware of the massive pivot that we've seen in terms of energy, especially around things like electric vehicles. Many different states, including California, have started to mandate that by near-term future, right, in 10 years or less, electric vehicles will be the only or preferred mode of transport that's out there. So what this means is there's a massive uptick necessary to meet this demand by battery manufacturing. We have to supply certain critical minerals, and particularly lithium. So while lithium is prevalent, the biggest problem we have with it is isolation purification. Hard rock mining is a solution. However, there's challenges that go around that. As you guys may have heard, there's projects like Thacker Pass done by Lithium America in Nevada, where there is a pretty good deposit there. However, the strip mining and refinement at that point will have a massive water pressure for the people in that area. So even though it's accessible, it's a huge displacement in terms of both people and resources. Second one is brine deposits. This is where you can potentially pump out underground aqueous reserves. The problem is you have to get rid of the water. That's very energy intensive and time intensive. Certain climates, that's just not possible. But in certain places like Chile or something that's very arid, it's possible. But again, it's very disruptive to the environment. So you're sort of replacing one problem for another. Now, what I've been involved with is a project done by a local company called Standard Lithium. What they're focusing on is actually working on a tail brine extraction. So what this does is take an existing aquifer that's currently being used as a bromine extraction facility. This is in southern Arkansas. So Lanxess Chemicals currently pumps a lithium-rich bromine solution. They pull the bromine out of it and currently just re-inject it. So this is something that's being done and has been done for more than 30 years. With very limited impact to the environment. So it's pumped up, remove bromine, put it back in the ground, no excess, the water balance sort of fits through there. What we did is we looked at this and said, well, there's a lot of lithium in that reserve. After you're done pulling the bromine out of it, give it to us, we'll strip the lithium and we'll just tag this part on. So it's not meant to have any other stress on the aquifer than just by simply doing this extra lithium extraction. So what that does, though, is that we get a lithium chloride solution here. Now that's where I come on board. Once we have lithium chloride, we still need to refine it and purify it, which is actually crystallization. Now, some of my specialty is in crystallization in the API pharmaceutical space. And we looked at this project of saying, well, look, you have that same challenges that we normally see if you're trying to purify chemicals for pharmaceuticals. You need high purity from a potentially varied feedstock. You need to really control this process. So this is where we got involved. What we built is a tool called SIFT. It couples a softening, so this is a charging of CO2. It allows a sort of a variable temperature crystallization under continuous process, and then finally isolation by filter pressure. It was meant to be a very simple end-to-end process. Where this folds over with my group, though, is that we tag in two major technologies. So first, we use in situ microscopy to actually look at the crystals themselves, see how they're developing, what they look like, what their native disposition is, particle sizes. At the same time, we look at the supernatant. We look at what's left over after we deplete the lithium from this point by ion chromatography, and that's using an online HPLC kind of system that we've done before. What this does is take the normal refining process, which is actually a very extensive reprocessing part, and that takes time, that takes energy, that takes water, and we've really just short-circuited it. By understanding how to natively do that crystallization well, we charge something like sodium carbonate. We do the crystallization, we end up with very high purity lithium in a much, much shorter workflow than was normally entertained. Well, why this is a difficulty is because typically we can control what the concentration of lithium in the brine is, and from there we have a solubility profile. The problem is the impurities that come with it are varied and they change depending on batch to batch, particular parts of the aquifer. As the process upstream changes, depending on even on the bromine plant, downstream can be affected. So what you need is some way of actually manipulating and understanding where on this play field you actually are. Why this matters so much is because the crystallization process, understanding what's in there, if you don't do the crystallization correctly, what you get are these high dense agglomerates, which actually trap material and make the lithium substandard for battery manufacturing. If we have a dynamically controlled process that understands what our starting state is, it's easy to sort of have no additional operation, but still high purity at the end. So where everybody else sort of takes a conventional varied material, spends a bunch of time making it to a very specific feedstock, which they then carry out the crystallization, we want to look at this as a way of adaptively doing the crystallization. So again, what you use, something like the in situ microscopy. On the top are the agglomerates I spoke of. They look like haystacks where they stick together as these kind of spike balls. Those have very high impurity incorporation, versus if we do it correctly, we end up with the crystals at the bottom. These are on the same scale. It's just what we have is very low surface area, very small contact areas between them. So really high purity needles. That's also possible because we know what's in the solution phase. The ion chromatography actually informs the system. So the actual plant itself, what we built functionally is this massive robot. The actual plant is a sort of two semi-trailer skids pushed together to be a fully end-to-end crystallization skid that's enabled by this online crystallization. What we can do is take really different feedstocks, one with a lot of calcium versus one that's actually potassium, strontium, and silicon sort of fouled. And we end up with the same high purity material from both of them because the system can adapt to those different conditions. At the same time, we don't have to just start with brine. We can actually charge the process with solid feedstocks, and that's not something that the same sort of worksheet from other processes can do. Usually they're designed to take solids and recrystallize them, or liquid brine and recrystallize them. Our system, it can be done either. We can actually charge it with different material. We've proven that out. And from there, this is actually an old data now. And the actual sort of scale up in time, actually, we did this during COVID. We were doing 15 kilogram purifications at very high purity. Now that it's been up and running for several months, we actually do between 15 and 20 kilograms a week. So it's really cool to see something like this reduced to practice. And again, it's only possible by having this automation in the back end that's adapting to circumstances on the fly. So again, really with that, massive thanks to my group. The work that I presented here today, so I've been doing most of the lithium work along with Shad over here at this point. The work that is presented in terms of the amidation chemistry, that's really Leo and Andrew Yusuke, and the work at the very beginning, talking about how we can sort of turn these automated tool chains in place. Luke is really the the genius behind this. He's actually a computer scientist heading into graduate school in that space right now. But again, super thankful to everybody in my group and super thankful for the time today to kind of bring you up to speed on what we've been doing, and happy to discuss anything else from this point. Thanks, guys.
Thanks, Jason. Really wonderful talk. I have several questions, but I'm going to see if we can open this up. So I think if the attendees want to either put their question in the chat, alternatively, I think that might be the easiest way to do it. And while we're kind of hearing some questions, I guess, Jason, you could pick any of the kind of case studies that you showed me, but you had, the one slide that you kind of nicely dissected where you had, an arm, you had the broken down robotic pieces into different sections.
Yeah.
Give the audience a sense of the cost, right? Like I guess, have, been investing in automation, and I guess what is some of the pieces and where you guys are looking at, where you're buying different arms, you're buying different kind of solid dispensers. What's the typical cost of kind of this flexible automation, even on this slide that you have here?
Sure. And so again, there's not a really good single answer. As an example, the liquid handling stuff that we've done before, sometimes that's just what's called a Gilson 215. It's a very simple XYZ needle and a stick, right? That you can find on eBay for about $1,000, not a big deal. There's Opentrons, right? These are very simple, open source XYZ. Sort of think of it like a 3D printer with a syringe pump built onto it. So very cheap, right? Open part. Or you could actually take a full like free slate, which is like $500,000, right? So it really targeting what is both budget and what piece of tool will answer your question is the critical part. And that's where, again, I've spent most of my time, I think actually Javier, we even sat down on this too, having that conversation up front and not listening to a sales rep is where you start. Because there's a whole host. In general, if you are interested, let's say, if we go to something like this, when we started this, we had to put a slide after we'd spin coated it, and we needed to heat it to a certain temperature. Now, we could have bought a commercial annealing oven that had a serial controller and a ridiculous, particular PID thing. In the end, we decided, look, we have no idea where that spec is. We need to learn. So we took a hot, like just a heat gun, put a switch onto the back of it, a simple controllable solenoid. And now we have our own sort of pipe, a heat pipe oven that's controllable through this with an internal thermistor and a very, very simple PID control loop that's possible to drop on top of it. Over here, this was meant to be a spin coater. Instead of that, we took a high rate of spin vacuum chuck and then put a coffee can over the top of it. So starting simple, and again, this concept of fit to purpose could be done on the low end of hundreds to a couple $1,000 to kind of get an idea of what will work for you, because there's definitely over engineered as well too. And I think one of the problems that we have, and again, maybe I'm being over too specific, but biggest problem we have in the materials chemistry and in organic chemistry space is most of this stuff came from the life sciences. It's great if you're playing with cells, not so awesome if you're trying to spin coat palladium, right? So there's things you can learn from that particular field that is kind of more in this sort of mechatronics and early automation that doesn't have to be the full enterprise version of what you'd see in sort of like a really, really, really tricked out lab for cell culture or something like the Broad Research Institute or like that. To give you another point too, an arm, something like this SCARA arm system here is a really precise, ridiculously fast. This is a high-end type system, but it has a very limited range of motion. Side to side, up and down is what it does very quickly. But if we look at something more like our what we did with the cobotic systems like this guy, the Canova is actually a $12,000 cobotic arm. It's a 6-axis arm where there's a very open back end. They are a provider of this, and then you can go through a web interface, actually build out where those positions go. You don't have the same accuracy of necessarily something else like a nice CNC machine, but it's really fast to deploy. So there are some issues with, okay, it may not have 24/7 uptime. It may have a couple millimeters off here and there, but to try out, I just need to move things from and from really fast to deploy, right? And the other thing too is that what you stick on here, the end effectors, those are 3D printed fingers. So you can change those to any other design that you need, so it can interact with a lot of different things quickly. So usually what we end up doing is build a lot of stuff yourself, deploy it, and then start to upgrade on the fly as you start to really focus on what your experiment has to look like.
Very nice. So we have a question from Adam. Great talk. Controlling the automated and robotic workflows is one part of the equation. The other is how to tag, store, integrate, analyze, right, all the experimental parameters and in situ characterization data, which you're clearly aware of, to feed into the machine learning. So the question is, do you build your own software solutions, or how do you integrate that piece into your work?
Yeah, a little bit of both too. Most of the time, the data we bring in, and again, what we're learning off of, the first thing we put in place is something where a lot of JSON kind of format. So we just pass around information in that point. You have to build what looks like a cost function, something that says this piece of analytical information contains a piece of something that I care about. That was good versus bad, right? You need some kind of a ranking structure in that. So the first part of it really does kind of look more like a JSON kind of library in terms of what your experimental input is and what your analytical output is, weighed against some sort of a cost function. But at the moment, again, it does change depending on what your analytical interface is. As an example of the thin film one, we had to sort of take spectral data and do a measurement and then a calculation to come out with what we call our, good versus bad kind of part. The quick answer is, at the moment, I don't think that there's an enterprise single solution, but it's starting to come together. In fact, actually, what I'm part of right now is a consortium called the Acceleration Consortium, led out of the University of Toronto, where one of the things that's starting to be formalized is data standards. So in the experimental synthetic optimization space, if you've seen something called, Google was actually backing it, the Open Reaction Database. This is something that Connor Cooley out of MIT has sort of started doing. And what he's basically saying is, all synthetic procedures for organic chemistry need to be systematized. In the same way that we saw, SI tell us that, look, if you're going to publish something, you need to prove mass spec, NMR, blah, right? That has to be part of it. You're starting to see the data handling, what gets fed to an algorithm, and actually what the instructions come back in, starting to fall into these systematic ways, which means database structure is starting to becoming defined so that we can have data portability. One more quick pump too. I am the associate editor of an RSC journal called Digital Discoveries, and we've started to have a data integrity policy, which means if you submit to this journal, you need to actually have something that is a fully capable, readable database and also open data that somebody else could actually look at and make use of. So you're starting to see this kind of propagate. As people start to use and digest ML a lot more, it will start to fall into several standards that are portable between different spaces. That includes analytical data as well.
Great. And we have one more question from a student. Thanks for the interesting talk. And I think this gets to, something you can appreciate, Jason, is how do you train chemists that don't have robotic or coding backgrounds to create and then use these systems? Absolutely.
That's number one. You have to find the early adopters first, but that's the cool part too. So as an example, the person I identified before, Leo is a fully dyed-in-the-wool synthetic organic chemist, flash columns, nothing robotics. Python and R are phenomenally accessible languages as long as you have the right community. So what we start to see is organic chemists, once you see capability, like the system is set up, it's ready for them to run. They just need the very simple push here, do this, stuff happens. After they start to see what you could do, they'll spend a bit of time learning a little bit of Python so they can start to say, without talking to the comp guys, I just want to change my volume, or I want 2 starting materials. And that's easy. That's a copy and paste. It takes time, but the best way to sort of to link into it is you need to embed yourself as part of an interdisciplinary group, because it's the same thing. The computer scientists, to them, DMSO, DCM, and triphenylphosphine or trimethylphosphine are all the same thing. And those are drastically different. On our side, we jump up and down in terms of air sensitivity, water sensitivity, and it's that cross-education about what matters to both. And the language that's involved is something we're really working on. But the simple point I'd say is give somebody the capacity, give a chemist the capacity to do these kinds of things, and they'll realize that investing a bit of time to bridge that gap or come up with a common language is well worth it for both sides.
Well said. Wonderful. If there's no other questions, I think let's thank Jason one more time. Jason, I think everyone's giving some high fives on an excellent talk. Really, this really did hit a lot of topics that's important to us. So thank you so much. It's been spectacular.
Thanks so much. Yeah, really appreciate it.